Levitation optomechanics is an interdisciplinary field combining optics, mechanics, and quantum physics to study the interaction between electromagnetic fields and levitating mechanical objects. Unlike conventional optomechanics, where mechanical resonators are physically anchored, levitation optomechanics involves particles trapped in vacuum using light or electromagnetic fields. These systems achieve ultra-low damping and high mechanical quality factors, enabling precise control and measurement of mechanical motion. This field also explores quantum phenomena, aiming to bridge classical mechanics with quantum mechanics by using tightly focused laser beams, optical tweezers, to trap silica nanoparticles in vacuum. Researchers have isolated these particles from thermal and vibrational noise, achieving near-perfect mechanical oscillations. It's like using a perfectly still hand to hold a delicate object without touching it, ensuring no external forces disrupt its balance. Levitodynamics is a specialized branch of optomechanics, focusing on levitating micro and nanoparticles in vacuum. The absence of clamping in these systems minimizes mechanical losses and environmental coupling, leading to exceptionally high quality factors, above 10 to the power 8 at room temperature. This isolation allows for experiments in quantum mechanics and high precision sensing. Levitodynamics provides a testbed for studying quantum coherence, decoherence, and the boundary between quantum and classical systems. Recent experiments have demonstrated the ground state cooling of levitated nanoparticles, allowing the study of quantum ground state fluctuations in mesoscopic systems. It's like suspending a pendulum in a vacuum chamber where it can swing indefinitely without air resistance or friction to slow it down. Macrocavity optomechanics involves large-scale optical cavities that trap and manipulate levitated particles. These cavities enhance light-matter interactions by confining light in a high-finesse cavity, increasing the optical field's intensity and enabling precise control over the particle's motion. Macrocavities are critical for detecting minute displacements and forces, making them ideal for large-scale systems like gravitational wave detectors. In the LIGO experiment, macrocavity optomechanics detects distortions in space-time caused by gravitational waves by measuring subatomic displacements in the mirrors, leveraging optical cavities for amplification. It's like using a magnifying glass to focus sunlight, amplifying its intensity on a small point for greater effect. Nanocavity optomechanics focuses on nanoscale optical cavities to trap and manipulate nanoparticles. These systems exploit the enhanced electromagnetic fields within nanocavities to achieve strong coupling between light and matter, enabling the observation of quantum mechanical effects at nanoscale levels. Nanocavities are particularly useful for studying single photon interactions and quantum coherence in nanoparticles. Levitated nanodiamonds with nitrogen vacancy, NV, centers inside nanocavities enable precise measurements of spin photon interactions, which are crucial for quantum information processing. It's like confining sound within a small resonant chamber, where even the faintest whisper can be amplified to a perceptible level. Levitated nanoparticles serve as highly sensitive inertial and force sensors due to their isolation from environmental noise and ultra-high mechanical quality factors. These systems can detect extremely weak forces, such as gravitational or electromagnetic interactions, making them suitable for precision measurements in fundamental physics and applied sciences. They are also used in accelerometry and torque sensing. Levitated nanoparticles have been proposed to detect weak gravitational interactions in searches for dark matter, where even the slightest deviations from expected motion can indicate new physical phenomena. It's like using a feather to sense subtle air currents in a sealed room, where its lightness allows it to respond to the faintest of breezes. Paul traps use oscillating electric fields to confine charged particles, allowing for the stable levitation of these particles in vacuum. Unlike optical traps, which rely on photon momentum transfer, Paul traps leverage the interaction between electric fields and the particle's charge. This method provides an alternative platform for studying levitated particles, particularly in experiments requiring lower optical power or different manipulation techniques. Paul traps have been used to levitate single-charged nanospheres, enabling experiments on their rotational and translational dynamics with high precision. It's like juggling a charged bead using alternating electric forces, keeping it suspended in mid-air without physical contact. Optomechanical metasurfaces are engineered surfaces that can manipulate light and mechanical motion simultaneously. These metasurfaces combine the properties of metamaterials with mechanical resonators, allowing for enhanced optical trapping and control of multiple levitated particles. They are promising for applications in optical computing, sensing, and energy harvesting. Metasurfaces have been developed to trap and cool levitated particles more efficiently, enabling advanced manipulation of their mechanical and quantum states. Imagine a flexible trampoline that not only supports objects, but also actively changes its surface to control how they bounce and move. Levitodynamics provides a unique platform for exploring the transition between classical and quantum mechanics. By cooling levitated particles to their quantum ground state and observing phenomena like quantum superposition and entanglement, researchers aim to understand how classical behavior emerges from quantum rules. These experiments test foundational principles, such as the role of decoherence in the quantum to classical transition. Experiments with levitated silica particles have shown quantum mechanical behavior, such as energy quantization and zero-point fluctuations. Even in mesoscopic systems, it's like observing a pendulum that behaves as a solid object at large scales, but starts to show wave-like properties when cooled to near absolute zero. Beyond simple translational motion, levitated particles exhibit internal degrees of freedom, including rotations, vibrations, and spin dynamics. Studying these internal dynamics provides deeper insights into the particle's quantum properties and potential applications in quantum sensing and information processing. For example, nanodiamonds with NV centers exhibit coupled spin and mechanical states that can be precisely controlled and measured. Levitated nanodiamonds allow the study of quantum spin dynamics under controlled conditions, providing a pathway for quantum memory and sensing applications. It's like studying a spinning top not just for its motion, but also for the internal vibrations and alignments of its parts, revealing more complex behavior. Levitodynamics is poised to revolutionize our understanding of quantum mechanics, sensing technologies, and precision measurements. Its ability to isolate particles from environmental noise while maintaining control over their mechanical and quantum states makes it a versatile tool for both fundamental research and practical applications. Future advancements could include the development of quantum networks, ultrasensitive gravitational wave detectors, and advanced quantum computing platforms. Levitated qubits could become a cornerstone of quantum computing, leveraging their isolation and coherence to achieve superior performance compared to traditional qubit systems. The field of levitodynamics is like discovering a new set of precision tools that can measure, manipulate, and explore the fundamental nature of reality with unparalleled accuracy.